All right, diving in today. Structural equilibrium. Super interesting stuff. You sent over this chapter, and I really want to dig into how engineers figure out what's going on inside those complex structures, trusses and frames and all those things. How do they make sure bridges don't just fall down?
Yeah, it's fascinating, right? And the funny thing is, those basic equilibrium ideas we've talked about before, they still totally apply. But when you start connecting things together, it gets a lot more complicated. You need a strategy, a way to break it down so you don't get lost in all the forces going on.
Totally. And it looks like this chapter lays out a few different methods for doing just that. I'm thinking we could take a look at three of them, kind of follow the flow of the chapter. So starting with the method of joints, then hitting the method of sections, and then finally wrapping up with how to analyze frames and machines. Sound good.
Sounds like a plan.
Awesome. All right, so before we even get into those methods, the chapter starts by talking about, well, different kinds of structures, right? We've got trusses, frames, and machines. Can you break down those categories for us? Like, what makes each one unique?
Yeah, for sure. So trusses, those are structures made up of these slender members, often connected in triangles, like you see in bridges or roof supports. And the big thing with trusses is that those members are designed to deal mainly with axial forces. So think tension, like pulling on a rope, or compression, like pushing on a strut. Those forces are acting along the length of the member.
Ah, okay. So those triangular shapes are key to how they handle those forces, right?
Yeah, exactly. Triangles, they're super rigid. So by connecting the members in triangles, trusses can be really stiff. And they can handle big loads over long spans, all using those tension and compression forces.
Okay, so trusses, slender members, triangles, mostly axial forces. Got it. Now, what about frames? How are they different?
So frames are also rigid structures, just like trusses, meant to support loads. You see them in buildings, vehicle frames, that sort of thing. The main difference is that frames have at least one, what we call a multi-force member. And unlike those two force members and trusses that only deal with axial loads, multi-force members, they can have bending moments, shear forces, and axial forces all at the same time. Imagine a bookshelf holding a bunch of books. It's bending, right? Not just being compressed or stretched. And the connections in frames are often more rigid than the pins we see in trusses, which also contributes to those more complex internal forces.
Gotcha. So more complex loading going on in frames. Makes sense. And then we have machines. Those sound like they're where things get really interesting.
Yeah, machines, they take the ideas from frames and add movement. Their main purpose is often to give you this mechanical advantage, basically multiplying force, like pliers gripping something or a lever lifting a heavy object. They have multi-force members, just like frames, but it's their ability to move and transmit those forces through linkages that really sets them apart.
Okay, so trusses are stationary, axial forces. Frames are rigid, more complex internal forces. And then machines, they move, also have those multi-force members. And often they're designed to make our lives easier by boosting our force. Now, the chapter talks a lot about two-force members. They seem pretty important for truss analysis. What exactly are they?
Well, it's pretty straightforward. A two-force member is a structural piece that has, you guessed it, exactly two forces acting on it. And those forces are applied at only 2 points on the member, no other loads in between.
And why is knowing about these two-force members so helpful when we analyze trusses?
Because it simplifies things a lot. See, since it's an equilibrium with just those two forces, they have to be equal in size, opposite in direction, and they have to act along the line connecting those 2 points. So if you can spot a two-force member, you immediately know which way the force is going along the member's axis. That saves us a bunch of unknowns to solve for.
Oh, that's a huge help. The chapter also mentions that when we're starting our analysis, we usually assume all the unknown forces in a truss are in tension. Why do we do that?
It's basically just a convention, a consistent starting point. By assuming tension, drawing the arrows pointing away from the joints, we have a clear sign convention. Then when we do the math, if we get a positive number, we were right, it's tension. If it's negative, it's actually compression.
Yeah.
Just a way to keep things organized without having to guess the direction right off the bat.
So assume tension, and the math will tell us the truth.
Like it. Now, all these members, they connect at joints, right? And those joints are where forces are exchanged. And that brings us to Newton's third law, that good old every action has an equal and opposite reaction thing.
Exactly. You can't escape Newton. That law is fundamental to how forces work everywhere, including in our structures. So when one member pushes or pulls on a joint, that joint pushes or pulls right back on the member with the same force, just in the opposite direction. And understanding these action-reaction pairs, it's super important when we start drawing free body diagrams to isolate different parts of the structure.
Because you can't really see those internal forces until you start breaking things apart in your analysis, right? Right. It's like when you take something apart, you suddenly see all the little pieces and how they were fitting together. When we isolate a joint or slice through a member, we're basically revealing those internal forces that were hidden before. And the key is to draw those free body diagrams carefully, making sure those action-reaction pairs are shown accurately. If member AB is pushing on joint B, then joint B is pushing back on member AB with the same force in the opposite direction. Messing that up is a classic mistake in structural analysis.
Consistency is key. Okay, now the chapter digs into simple trusses. What makes a truss simple, and why is that a useful starting point?
Well, a simple truss is kind of an idealized model, right? It's made entirely of two force members, the connections are frictionless pins, and all the loads and reactions are only at those joints, no messy stuff in between. This simplified view lets us use basic static equilibrium to figure out those unknown forces.
And the chapter gives us this equation, 2J areal R plus M, to see if a simple truss is statically determinate. What does that even mean, and how does the equation help us figure it out?
Static determinacy basically means we have just enough equations to solve for all the unknowns. And for a flat, simple truss, at each joint we've got two equations. Sum of forces in x equals 0, sum of forces in y equals 0. So 2J is the total equations. On the other side, R is the number of unknown reactions at the supports, and M is the number of members, each with an unknown force. If 2J equals R plus M, we're good, we can solve it.
So it's all about balancing equations and unknowns. But what if it doesn't balance? The chapter mentions unstable and redundant trusses.
Right. If 2J is bigger than R plus M, that suggests we might have an unstable truss, not enough members to hold it together once you take away the supports. On the other hand, if 2J is smaller than R plus M, that means we've got extra members, more than we strictly need for stability. That's a redundant truss. It might be harder to analyze with simple statics, but in the real world, those extra members can make it stronger because if one fails, the others can pick up the slack.
And that brings up a really important point the chapter makes, the danger of simple trusses.
Yeah, exactly. Simple trusses, they have just enough to stand up, but if one critical member fails, there's no backup. It's what we call fracture critical. It can lead to a cascading failure, and that's how you get bridge collapses like the Silver Bridge disaster. It really highlights how important these concepts are when you're designing structures.
A very real reminder of the stakes. Okay, before we get into the method of joints, the chapter talks about these zero-force members. What are they, and is there a way to spot them without doing a ton of calculations?
Yeah, zero-force members, they're like the flackers of the truss. They're there, but they're not actually carrying any load under a specific condition. Being able to spot them early on can really streamline your analysis. And the chapter gives us two handy rules.
Let's hear 'em.
Okay, rule number 1. If you've got a joint where only two members connect, and there's no load or reaction directly on that joint, and those two members aren't in a straight line, then both of them are zero-force members. Think about it. If they're just hanging there, not loaded, not in a line, they can't be doing any work.
Makes sense. If they're just chilling, they're probably zero force. What's the second rule?
Okay, rule number 2. If you've got a joint with 3 members, no load or reaction at the joint, and 2 of those members are in a straight line, then the third one, the one sticking out, that's a zero-force member.
The chapter uses figure 6.3.5 as an example. It shows joint B with members BA and BC in a line, and then BD coming in at an angle. So by rule 2, BD would be zero force, right?
Exactly. And that can then help you with nearby joints. If the BD is zero force, it's not putting any force on joint D, which might lead you to find another zero-force member there. It can really simplify things as you go along.
It's like finding shortcuts in the structure. But then there's this thinking deeper section about why engineers put those seemingly useless members in real-world designs. If they're not doing anything, why bother?
Right. It's a good question, and it highlights how our simple models don't always capture everything. First off, we often assume members are weightless, but in reality they're not. A vertical member might need help supporting its own weight. A zero-force member might be preventing sag. Also, slender members under compression can buckle, kind of like when you push on a straw, it bends sideways. So a zero-force member might be there to brace a compression member and stop it from buckling. And finally, real-world structures often have to handle different loading scenarios. A member that's zero force under one condition might be crucial under another.
So they're like backup dancers, ready to step in when needed.
Okay, we've covered trusses, two-force members, Newton's third law, simple trusses, and zero-force members. We're finally ready for the main event, the method of joints. How does this thing work?
So the method of joints, it's all about looking at each joint individually, like it's a tiny world of its own. All the forces there meet at that one point, so we only need to use force equilibrium. For a 2D truss, that means the sum of the horizontal forces at the joint is 0, and the sum of the vertical forces is 0. And since we've got two equations at each joint in 2D, that means we can solve for, at most, two unknown forces at a time.
Exactly. So we have to start at a joint where we know at least one force, maybe from an external load or a reaction we calculated earlier. And it can have no more than two unknowns. Then we solve for those, and those become knowns for the next joint we look at, and so on.
Like a chain reaction of solving.
Exactly. And the chapter lays out the steps pretty clearly. First, we make sure it's a determinate simple truss using that equation, 2J equals R plus M. Then we can get rid of any zero-force members if we want, just to simplify things. And if we need to, we might have to calculate those external reactions first by looking at the whole truss.
So we need a starting point, some knowns to kick things off. Then what?
Then we pick a solvable joint, one with one or two unknowns, and draw its free body diagram. Just a dot representing the joint. We show all the forces acting on it, external loads, reactions, and for each unknown member, we draw an arrow along the member, pointing away from the joint, assuming tension.
Then we unleash those equilibrium equations, right? Sum of forces in x equals 0, sum of forces in y equals 0, and solve for our unknowns.
Exactly. Positive means tension, negative means compression. Then we take those solved forces with the correct tension or compression and carry them over to the next joint. It's like dominoes. And if we calculated the external reactions earlier, we can use the last joint as a check. All the forces should be known by then, and if the equilibrium equations work out, it means we probably did everything right.
So method of joints, it's all about going step by step, joint by joint. But it sounds like it could get pretty tedious for big trusses.
Yeah, it can. Especially if you only need the force in a few specific members. That's where the method of sections comes in. It's like a shortcut.
Okay, the method of sections. Let's hear how it works. It sounds like a more efficient way to get those specific forces.
Basically, you take your truss and imagine slicing it into two parts. And you do this in a way that cuts through the members you're interested in. Then you look at one of those sections, usually the simpler one, and treat it like a solid object.
So instead of a joint, now we're looking at a whole chunk of the truss. And since it's a rigid body, we can use all three equilibrium equations, right? Sum of forces in x, sum of forces in y, and sum of moments, all equal to 0.
Exactly, and that moment equation becomes really useful here. If you're clever about where you take the moments, you can make some of the unknowns disappear, so you can directly solve for the force you want.
Okay, walk me through the steps. How do we use this method of sections?
Similar process to the method of joints. Make sure you have a simple truss, get rid of any zero-force members, and if you need to, calculate those external reactions first.
Then the big step, making the cut. How do we choose where to cut and how many members to slice through?
You want to cut through the members you need the forces for, but ideally no more than 3 at a time for a 2D truss, because each cut creates an unknown force, and we've only got 3 equations to work with. If you cut more than 3, you'll have too many unknowns. And remember, the cut doesn't have to be straight, just as long as it divides the truss into 2 pieces.
Got it. So we made the cut. Now we've got 2 pieces of the truss. What do we do with them?
Pick one, the one with fewer loads and reactions, and draw its free body diagram. Show all the external forces acting on that section, and then, for each member you cut, draw an arrow representing the force, pulling away from the cut, assuming tension.
Then we hit it with the equilibrium equations, right? Sum of forces in x equals 0, sum of forces in y equals 0, sum of moments equals 0.
You got it. And that moment equation, choose your pivot point wisely, and it can make things much easier. Negative answer means compression, as always.
The chapter says that if you need forces in multiple members, you might have to make more cuts, or even mix the method of sections with the method of joints.
Yeah, sometimes you got to get creative. But the point is, we've got these tools, and we can use the best one for the job. Or combine them. Flexibility is key.
Okay, so method of joints, step by step. Method of sections, more targeted. Now we've got frames and machines. The chapter says those are different beasts. Why is that, and how do we tackle them?
The big difference is those multi-force members. Remember, in trusses, we only have 2 force members, simple forces. But frames and machines, they've got members that can bend, twist, and have forces all over the place.
So if you cut through one of those multi-force members, you're opening up a can of worms, right?
Exactly. You might have 3 unknowns at the cut: horizontal force, vertical force, and a bending moment. And if you try to do the method of sections, Cutting through a bunch of those, you'll quickly have way too many unknowns for your equations. Same with the method of joints. Too many unknown forces and moments at those connections.
So we need a whole new approach then. How do we analyze these frames and machines?
We break them down, piece by piece, take the whole structure apart,
Mhm.
conceptually, and look at each member as its own little world. Draw a free body diagram for each one, showing all the forces and moments acting on it.
Sounds like a lot of diagrams.
It can be, but the key is Newton's third law. Those action-reaction pairs at the connections, they're what tie everything together. The force one member puts on another is equal and opposite to the force the other puts back. You have to show those forces consistently on your diagrams. If you mess that up, your whole analysis is shot.
So it's like a jigsaw puzzle, each piece a member with its own forces, and Newton's third law is the glue that holds it all together.
That's a good way to put it. And often, you have to solve a whole system of equations, using what you find from one diagram to solve another, and so on.
Okay, what are the steps for analyzing these things?
First, you got to see if the whole structure is rigid on its own, would it hold its shape without supports? Look for triangles, they help. If it is rigid, you can start by finding the external reactions. But if it's not, like a lot of machines that move, you skip that and go straight to the individual parts.
Step 2, draw a free body diagram for every single member. What do we need to show on those diagrams?
Everything acting on that member. External loads, any moments or couples, the weight of the member if it's important, forces from supports, and the forces and moments at every connection point. For two-force members, it's easy. You know the line of action. For multi-force members, you usually break the force into X and Y components because you don't know the direction yet. And again, Newton's third law, make sure those action-reaction pairs are shown correctly.
Then we write our equilibrium equations for each diagram. And finally, the big solve.
Right, it might involve some algebra, some substitution, but eventually you get those forces and moments figured out.
The chapter uses a toggle clamp as an example, which looks pretty complicated.
Yeah, the toggle clamp is a good one because it shows how to take a complex machine and break it down. Figure out where the external loads are, and then focus on those internal forces between the parts. For example, the force the link puts on the handle. That's an external force for the handle's diagram. But then on the link's diagram, you'll see the equal and opposite force from the handle. Action, reaction, inaction.
The chapter even points out a mistake in one of the diagrams, figure 6.6116, reminding us that we only include forces acting on that specific member, not internal forces from other parts.
Super important. Your free body diagrams have to be perfect, or your analysis will be wrong. And the solution for the toggle clamp example shows how you use those individual diagrams and the equilibrium equations to find the clamping force, the reactions at the pins, the whole 9 yards.
So we've covered a lot of ground. Method of joints, going joint by joint. Method of sections, slicing and dicing. And finally, frames and machines, breaking them down into their individual members and using Newton's third law to connect it all.
It all boils down to being systematic, knowing what kind of structure you're dealing with, drawing those free body diagrams like a pro, and then applying those equilibrium equations. And even though things get more complex with frames and machines, those basic principles of equilibrium, they never go away.
This has been really eye-opening. Thank you so much for breaking this down for us. And to our listeners, thanks for bringing us this awesome chapter. We hope you all learned a thing or two about how those structures around us stay standing, and maybe it even sparked some interest in digging deeper into the world of engineering. Thanks for joining us on this deep dive.